Okay, so before we move on to the first kind of straightforward applications of the chain rule, we stop and introduce some notation because this is something you may see. So the chain rule in Leibniz notation. So you know already that there are two ways of denoting, two ways of denoting the derivative. We use notation for the derivative. So if we let y be equals to f of u, where u is some g of x, some function of x, then we can write y prime in Leibniz notation. Leibniz is d dx, dy dx, which is, we've already seen, this is f prime of u at u times g prime of x. But remember that we can use the Leibniz notation for each one of these expressions. So df du times du dx. And in other words, we can write dy dx is equal to dy du times du dx. So this is the chain rule, and it's the exact same rule, just in Leibniz notation. And one thing I want to draw your attention to is that these things, these objects here, are not fractions. In particular, you cannot simplify this to obtain that. So this is incorrect. So you cannot simplify the d's, the notation here, du's here. So for instance, if I ask you during an exam, what do I get when I simplify the du's here, and you tell me the f dx, that will be incorrect. So the correct answer should be that you can't simplify the du's. They're not numbers, so these are not fractions. This is just notation for the derivative. Okay, so that's just for the for the notation that you may see in some places. And now we can move on to the very special cases of the chain rule. This is theorem 2, and these are the general power and exponential rules. First property here, and we're going to use Leibniz notation. The dx of some function g of x to the n is going to be equal to n times g of x to the n minus 1 times g prime of x. This is for any this is valid for any number n. And then the second property, which is, I mean, if you don't know these rules, nothing happens. I mean, it's just that you may waste time if you don't know them, but you can deduce everything from directly from the chain rule. So this is just e to the g of x times g prime of x. So let's try to prove just one of them, because, I mean, actually, let's prove both of them. F of u, the outside function in for all of the cases covered in part 1 of this theorem, is the power function u to the n, right? And g of x is just, really the inside function is some g of x. So g of x here to the n is just f composed with g, or f evaluated at g of x. So by the chain rule, we take the derivative of the outside function, evaluate at the inside function, and then take the derivative of the inside function and multiply everything. So this is dx of g of x to the n. And this is just f prime of g of x, right? G of x times g prime of x. That's just the chain rule. And this is equal to, and what's the derivative of f? Remember the power rule? Tells us that f prime is n times u to the n minus 1. So f prime here will be n times what's inside to the n minus 1. What's inside here is g of x to the n minus 1. And we multiply g prime of x, this by g prime of x, which is exactly what we wanted to show. This is what the rule here says, so we're in complete agreement with it now. So if you look at this and this expression here, they are the same thing. Okay, what about the second part? So the second shortcut to the second special case of the chain rule. E to the g of x is another composite function, is a function of the form h evaluated at g of x. What is h? Well, it's just e to what's inside. I mean, this is what we did to g. So h of u is just the exponential function at e to the u. So what's the derivative of e to the g of x? This is just h prime of g of x times g prime of x, which is just e to the g of x times g prime of x. right? What is h prime? H prime of u is just e to the u. What's the derivative of the exponential function? It's the exponential function itself. We'll learn that, so this will be e to what's inside, right? Which is exactly that, this first term. And g prime of x is just g prime of x. So we've actually shown the validity of these two shortcuts. So looking at some examples. With the first one, let's suppose that we want to find what is the derivative of cosine of x to the 100. So if f of x is equal to, so let me write this here. F prime of x will be equal to, so the solution, this is of the form some function of x raised to a constant power. Remember again, this applies to a function of x raised to a constant power. So the general power rule applies to g of x to a constant power. Okay, so I'm gonna give I'm gonna give this example, and then I'm gonna comment on what you should not do. So here n, so we apply the first part of theorem 2 to what is g of x? If you go back, g of x is the function here, the function that's being raised to a power. So g of x is g of x to the n. So g of x here will be cosine of x, and n will be equal to 100. N will be equal to 100. Okay, so according to the rule, what is cosine of x then to 100 prime? This is n, or 100 in this case, times cosine of x times 100 minus 1. This is what the rule says, so n minus 1, times the derivative of what's of this g of x. The derivative of this g of x is, what is the derivative of cosine of x, do you remember? Is equal to minus sine of x. We covered that last week. So this is equal to 100 times cosine of x to the 99 power times minus sine of x. Or what's the same? Minus 100 times cosine of x to the it's not x that's being raised to 99, but cosine of x, rather cosine of x. This is what the rule says. And this times sine of x. Okay, so this is the first application. I wanted to stop and say something about. So what about this application? Some remark. What about computing the derivative I'm sorry. What about computing the derivative of, say, a cosine of x to the sine of x, this prime? If you tell me that you can apply the power rule here, that would mean that we could be able to just do this. So applying rule and getting cosine of x to the sine of x prime is equal to, well, we bring the exponent down, so there will be sine of x times cosine of x times sine of x minus 1. This would be completely wrong. But I mean incredibly wrong. The rule only applies to functions raised to a constant exponent. So something of the form e.g. cosine of x, like what we did, like cosine of x to, and it can be any power. So pi, for example, is acceptable. Pi is a number. It's not a function, so it does not depend on x. Now we can also apply to, say, x cubed plus 2x plus 3, say, raised to the power 5. And say 1 over x to the, x squared plus 7 to the power of e. Say e is a number, so that's acceptable as well. So all of these are correct applications. So this is a function of x raised to a constant power. So pi here. This is a polynomial raised to the power 5, which is a number. And this is the same. This is the same as 1 over x squared plus 7. All of that raised to the e, to the power e. And e is just a number. So this is e is not a function. So those are all correct applications. To find, I mean, we can still differentiate something like that. We can differentiate. So we can differentiate, so we can compute the derivatives of expressions like the one above, so like cosine of x to sine of x, by another technique, by using logarithmic differentiation. So what's the deal here? Remember, applying the generalized power rule to functions raised to functions is incorrect. The generalized power rule, just like the power rule, only applies to functions raised to a number. And now I'm telling you this, so getting ahead of myself a little bit, but I want to point out that this is what we're going to learn. We'll still be able to differentiate expressions like cosine of x to the sine of x, and we'll actually be asked to do that for the second midterm. But that will appeal to something that's called logarithmic differentiation. Okay, so that's my so those are my two comments that I wanted to make. Now, so now let's look at one other application. So one other example. I said that we're going to do some examples. So one is this one. This uses the generalized power rule. Now, what about the other rule? So the generalized exponential rule. So what is the derivative of e to the cosine of x? According to the formula, this is just e to the cosine of x times g prime of x, which is the derivative of cosine. And what is the derivative of cosine? Is minus sine. So we can write this as minus sine of x, which is the derivative of cosine, times e to the cosine of x. And this is our second application. And we'll continue in the last video for Tuesday.